That's what makes Yellowstone genuinely unsettling, separate from the disaster movie version. Not that it might erupt, but that we're watching something we don't fully understand, with instruments we've only had for 25 years, hoping to read signals in a system that operates on timescales of hundreds of thousands of years. There's a team of scientists at the USGS whose entire job is to watch for signs that any of this is approaching. They work out of the Yellowstone Volcano Observatory, which publishes a bulletin every week. The bulletin almost always says the same thing. Activity is within normal background levels. Elevated, but normal. The magma is moving, but it moves all the time. What the bulletin cannot say, what no instrument currently built can say, is how much warning you'd actually get if that answer changed. That's the third most immediate consequence of a Yellowstone supereruption. The first two, pyroclastic flows covering several hundred kilometers around the caldera and ashfall across the entire continental United States, are faster and more localized. The atmospheric effect is what reaches the rest of the planet. If Yellowstone erupted tomorrow, the first thing most Americans would notice is not fire, not ash, not yet. The sky above Wyoming would change color, a sound with no good comparison in modern experience. Then, within hours, the stratosphere would begin filling with sulfur dioxide at a scale that hasn't occurred since human civilization existed, and sunlight across the northern hemisphere would start dimming within weeks. By the time ash reached the East Coast, the growing season in the American Midwest would already be gone for that year, possibly for several. The Lava Creek eruption, the event that created the current caldera, happened at a moment when the Earth's surface looked quite different from today. The Great Plains were grasslands roamed by species that no longer exist: mammoths, giant short-faced bears, horses. Modern humans had not yet evolved. Whatever creatures were living within range of Yellowstone at that moment left no record, because there was nothing left to leave a record in. The ash field from that eruption covered what is now Iowa, Nebraska, and most of the states between. Geologists still find it, a distinctive gray layer in road cuts and riverbanks across the American interior, identifiable by its chemical signature. It is called the Lava Creek Tuff, and it is several meters thick in places. Not several centimeters, several meters. There have been two major eruptions before that one, both larger. The first, roughly 2.1 million years ago, ejected an estimated 2,500 cubic kilometers of material. The second, 1.3 million years ago, was smaller. Still catastrophic by any human comparison, just less so than the others. Each eruption left a caldera. Each caldera is now a feature of the landscape, buried under subsequent geology. The modern Yellowstone Plateau sits on top of all three. When geologists first seriously studied Yellowstone in the 19th century, they kept looking for the volcano. They expected a cone, something like Vesuvius or St. Helens, a mountain with a crater at the top that you could point at and say, "There." It took decades to understand why they couldn't find it. From ground level, Yellowstone looks like a national park. Mountains and forests, geysers, bison. Beautiful in the way that very old places tend to be. No obvious summit, no obvious crater. Because the crater is the entire plateau. 70 kilometers across, the floor of a collapse so total that the volcano consumed itself. The reason is that Yellowstone is a caldera, the collapsed remains of a volcano so large that when it last erupted, the entire structure above the magma chamber fell inward. What you see now, the broad plateau of the park, is the floor of that collapse. The crater is the landscape. The Yellowstone Hotspot has produced three major eruptions in the last 2.1 million years. The first, 2.1 million years ago, was the largest, ejecting roughly 2,500 cubic kilometers of material. The second, 1.3 million years ago, was smaller. The third, the one that created the current caldera, happened about 640,000 years ago. Geologists tracking the pattern noticed the intervals between eruptions are not consistent, The gap between the first and second was about 800,000 years. The gap between the second and third about 660,000 years. This gets repeated a lot in popular coverage, usually to suggest we're somehow overdue. The reality requires saying this directly. Eruption intervals at Yellowstone are not regular enough to predict the next one from the last. The hotspot doesn't work on a schedule. It works on geology. What the hotspot does, reliably, is sit there. Beneath the crust of North America, a column of unusually hot mantle material rises and punches through the plate above it. The North American plate drifts slowly southwest over this column, which is why the track of ancient eruptions stretches across Idaho and Nevada. The hotspot doesn't move, the continent does. Yellowstone is just the current address. The hotspot track runs like a scar across the American Northwest. If you draw a line connecting the ancient calderas left by previous Yellowstone eruptions, it runs southwest through Idaho and into Nevada, a record of where the continent was sitting when each eruption occurred. The Snake River Plain, the broad, flat valley that cuts through southern Idaho, is essentially the floor of a series of collapsed calderas left behind as the North American plate moved over the hotspot. The landscape looks unremarkable from the highway. It is one of the most volcanically significant landforms in North America. Hotspot volcanism is different from the kind most people associate with subduction zones, places like the Cascades or the Andes or the Pacific Ring of Fire, where tectonic plates collide and one dives beneath the other. At a subduction zone, the process is relatively predictable. Plate goes down, rock melts, magma rises. At a hotspot, the heat source is deeper, less well understood, and, critically, not linked to plate movement in the same way. The North American plate doesn't control the hotspot. The hotspot just sits there. The continent moves over it, and what happens above it depends on what the crust looks like at that particular point. Currently, the crust above the Yellowstone hotspot is thick and cold enough to cap the system effectively. That can change. The numbers involved in a Yellowstone supereruption are so far outside ordinary human experience that they stop functioning as numbers. They become abstractions. The 1991 eruption of Pinatubo in the Philippines ejected roughly 10 cubic kilometers of material and lowered global temperatures by about half a degree Celsius for 2 years. One of the largest eruptions of the 20th century. A Yellowstone supereruption would eject somewhere between 1,000 and 3,000 cubic kilometers. Not 10, 1,000. Ash would cover the entire continental United States to some depth. In Wyoming and Montana, the depth would be measured in meters. In states further away, in centimeters. But even a thin layer of volcanic ash disrupts agriculture, clogs engines, contaminates water, and collapses roofs when it gets wet. The finest particles stay in the atmosphere for years, reflecting sunlight back into space and cooling the planet below. The last Yellowstone supereruption left a layer of ash that geologists can still find across the Great Plains. It is called the Lava Creek Tuff. In some places, it is several meters thick. There are no human civilizations that experienced that eruption, no written records, no eyewitness accounts. The evidence is just a layer of gray rock running through hillsides across the American interior. That is what a Yellowstone supereruption leaves behind. Not history, geology. The Mount Pinatubo eruption in 1991 offers a useful reference point for what the atmospheric component of a large eruption actually does. In the 18 months following Pinatubo, global average temperatures dropped by roughly half a degree Celsius. That sounds small. In agricultural terms, it translated into measurable reductions in crop yields across the northern hemisphere, a temporary hole in the ozone layer, and disrupted monsoon patterns across South Asia. Half a degree from 10 cubic kilometers of ejected material. A Yellowstone supereruption would eject between 100 and 300 times that volume. The comparison that puts the ashfall in sharper focus is the 1783 Laki eruption in Iceland. Laki ejected roughly 15 cubic kilometers of material, larger than Pinatubo, but still tiny relative to Yellowstone. The haze it produced across Europe that summer was dense enough to kill crops across the continent. An estimated 10,000 people died in Iceland, roughly a fifth of the entire population at the time, mostly from famine and fluorine poisoning in the ash. In Egypt, the Nile flood failed that year, contributing to a famine that killed roughly 1 in 6 Egyptians. One Icelandic volcano, 15 cubic kilometers. The consequences stretched from the Arctic to Africa. The Yellowstone Volcano Observatory was established in 2001, which means systematic, continuous observation of the caldera has existed for only about 25 years. In geological terms, that's nothing. In practical terms, it's given us a picture of a system in constant motion. The caldera floor has been rising and falling in cycles. Between 2004 and 2008, it rose by about 70 centimeters, the fastest uplift ever recorded at Yellowstone. Then it slowed and partially subsided. This kind of ground deformation is driven by the movement of hydrothermal fluids and magma beneath the surface. It doesn't necessarily signal an eruption is coming, it signals the system is alive. Yellowstone averages between 1,500 and 2,500 earthquakes per year. Most are too small to feel. Occasionally, swarms occur, clusters of hundreds of small earthquakes over days or weeks. In 2017, a swarm of more than 2,000 earthquakes hit the park over 3 months. It was the largest swarm recorded since monitoring began. The USGS concluded it was caused by movement of hydrothermal fluids, not magma. No eruption followed. Old Faithful erupts because superheated water trapped in underground channels flashes to steam when pressure drops. The water feeding the geyser systems can exceed 300 degrees Celsius. It doesn't boil at the surface because it's under pressure. When it reaches a vent, the pressure drops and the water becomes steam almost instantaneously. There are roughly 10,000 of these hydrothermal features in the park: geysers, hot springs, mud pots, fumaroles. Together, they represent the largest concentration of surface hydrothermal activity on Earth. All of it is venting energy from what sits below. The USGS scientists who work on Yellowstone are not alarmists. They push back firmly against the idea that an eruption is imminent, or even particularly likely within a human lifespan. But not particularly likely in any human timescale and safe are different things. The gap between those two phrases is where most of the public conversation about Yellowstone actually lives. One of the stranger features of monitoring Yellowstone is that the thing scientists are most worried about is not the most dramatic thing they can see. The geysers and hot springs are the visible surface of the system. Impressive, photogenic, the reason millions of people visit the park every year. But from a hazard perspective, they're almost a sideshow. The real data comes from ground deformation sensors and seismographs that detect movement in the deeper system, far below anything that produces a visible feature at the surface. The 2004 to 2008 uplift episode is worth dwelling on because it generated the kind of concern that the observatory is built to evaluate. The caldera floor rose at a rate that, if sustained, would have been alarming. It wasn't sustained. It slowed, partially reversed, and the system returned to its background state. But the episode demonstrated something important. The system can change relatively quickly by geological standards. Weeks, not centuries. The signal of a genuine buildup toward an eruption would likely look something like that uplift episode, only faster and without the reversal. The challenge is distinguishing one from the other while it's happening, not in retrospect. Yellowstone also experiences what geologists call hydrothermal explosions, events that have nothing to do with magma, but everything to do with the superheated water beneath the surface. In 1989, a hydrothermal explosion in the Porkchop Geyser area sent debris flying across a 50-meter radius. In geological history, much larger explosions have left craters several kilometers across. Mary Bay, on the northeastern shore of Yellowstone Lake, is the scar of a hydrothermal explosion that occurred roughly 13,000 years ago, one of the largest known. These events can happen with almost no warning and are essentially independent of the deeper magmatic system. One thing Yellowstone coverage gets consistently wrong is the idea that a supereruption would come without warning. It wouldn't. The signs would be extreme and prolonged. Ground deformation measured not in centimeters, but in meters. Earthquake swarms that don't stop. Dramatic changes in hydrothermal activity. Scientists would likely have weeks, possibly months, of escalating signals before any major eruption. Likely have warning and definitely have warning are different things. And weeks of warning is not the same as enough time to evacuate the American interior. The immediate effects of a supereruption would begin with pyroclastic flows, superheated mixtures of gas and rock moving at several hundred kilometers per hour, covering an area of perhaps several hundred kilometers around the caldera. Nothing in that zone survives. Beyond the pyroclastic zone, ashfall, thick near the source, thinner with distance, but significant everywhere across the continent. The Mississippi River watershed would be compromised. The grain belt of the American Midwest, which feeds much of the world, would be buried under ash for years, possibly decades. The third effect is atmospheric. Sulfur dioxide released into the stratosphere forms sulfate aerosols that reflect sunlight back into space. Global temperatures drop. Crop failures spread wherever sunlight limits agriculture, which is most of the temperate world. This is the mechanism that destabilized empires when Tambora erupted in 1815, when Laki erupted in 1783, when volcanic forcing triggered the catastrophic climate of 536 AD. At Yellowstone scale, the effect would be larger and longer. Scientists who study supervolcanoes are genuinely uncertain about exactly how bad it would be. Some models suggest civilization-ending consequences. Others suggest catastrophic but globally survivable outcomes. The accurate answer is that we don't know, because no human civilization has experienced one. The sequence of events in the first hours of a major Yellowstone eruption would be unlike anything in recorded human history. The initial explosion would be audible across most of the continental United States. Acoustic waves from eruptions of this scale have historically been recorded thousands of kilometers away. The ash column would reach the stratosphere within minutes and begin spreading downwind. Prevailing winds across the United States generally run from west to east, which means the densest ash fallout would move toward the Great Plains and Midwest in the first hours, reaching the East Coast within a day or two. Emergency response at that scale would face challenges that have no modern precedent. The interstate highway system crosses the heaviest ashfall zone. Aircraft cannot fly through volcanic ash, jet engines ingest the particles and fail. The electrical grid across the affected states would be compromised as ash coats insulators and causes short circuits. Water treatment facilities would struggle as ash contaminates reservoirs. And all of this would be happening simultaneously across a region containing tens of millions of people. FEMA has conducted planning exercises for Yellowstone scenarios. The conclusions of those exercises are, to put it gently, sobering. More importantly, the magma chamber beneath Yellowstone is not currently in a state volcanologists would associate with imminent eruption. Monitoring data show the magma is mostly solidified. Estimates suggest the melt fraction of the chamber is between 5 and 15%. Magma systems typically need to be significantly more liquid than that to produce a major eruption. At present, the Yellowstone system reads more like a sleeping giant than a charging one. There is also a serious scientific case that Yellowstone may never produce another supereruption. Some volcanologists argue that the hotspot has been gradually weakening as the North American plate's composition changes above it. The three eruptions of the past 2 million years were progressively smaller. This is not a consensus view. The data are genuinely ambiguous. But it is a position held by credible researchers working from real evidence. What Yellowstone is more likely to produce, on a shorter timescale, is a hydrothermal explosion or a lava flow event. Neither would be pleasant. Neither approaches the planetary scale of a supereruption. Hydrothermal explosions have happened at Yellowstone in historical and geological time, essentially giant steam blasts, devastating within a localized radius, but not world-altering. Lava flows are local events. Yellowstone is a remarkable active system under continuous observation. The scientists watching it are not quietly hiding alarm. They are genuinely uncertain about what the system will do next, but uncertain and alarming are not the same word. The 5 to 15% melt fraction figure deserves some unpacking, because it's the number that most directly addresses the "is it going to erupt soon?" question. To produce a major eruption, a magma system generally needs to be largely molten. Estimates vary, but many volcanologists put the threshold somewhere above 50% melt. At 5 to 15%, the Yellowstone system is essentially a hot, partly crystallized mush, not a liquid reservoir under pressure. It would need a significant injection of new magma from below, or some other mechanism to rapidly increase the melt fraction before an eruption became physically possible. Where serious scientific disagreement exists is not on the probability of near-term eruption. That's low, and most researchers agree, but on the long-term trajectory of the system. One school holds that Yellowstone is in a declining phase. The three eruptions were progressively smaller, the intervals are not getting shorter, and the hotspot may be weakening as the lithosphere above it thickens. A competing view holds that the system's behavior over three eruptions is not a sufficient sample to draw conclusions about long-term trends, and that the next eruption, whenever it occurs, could be larger than the last. Both positions are defensible with the available data. Neither has won the argument. What we don't know is when any of this becomes something else. The transition from active background to approaching eruption is something we've never observed at a supervolcano in real time. We have records of what smaller volcanoes do in the weeks and months before they erupt. We have geological evidence of what happened before Yellowstone's previous events. But a geological record and a live data set are fundamentally different things. We are watching something we cannot yet read with confidence, with instruments running for less than 3 decades, looking for patterns in a system that operates on timescales of hundreds of thousands of years. The question people want answered, is it going to erupt, is not one science can currently answer with confidence. The best available answer is, not obviously soon, and we'll see the signs if it starts heading that way. That is a reassuring answer. It is also, depending on how you think about it, not fully satisfying. The scientists monitoring Yellowstone describe their work as watching for something they hope never happens. They keep watching because the alternative is worse. What would actually constitute an alarm signal at Yellowstone is a question the observatory has thought about carefully. The short answer is that no single measurement would trigger an alert. It's the pattern and combination of measurements that matters. The alarm pattern would look something like this: rapid ground uplift combined with a spike in earthquake frequency. Significant increases in deep gas emissions, particularly carbon dioxide and hydrogen sulfide, plus measurable changes in hydrothermal output. Together, those signals would suggest the system was moving toward a new state. None of those signals currently exceed background. The deeper problem is that we've never actually watched a supervolcano go from dormant to active in real time. Everything we know about the precursor signals of large eruptions comes from smaller systems, stratovolcanoes, calderas like Campi Flegrei in Italy or Taal in the Philippines that have produced significant unrest in historical time. Scaling those observations up to a system the size of Yellowstone is an extrapolation, not a measurement. It's a reasonable extrapolation based on solid physical principles, but extrapolation is what it is. Yellowstone features prominently in discussions of global catastrophic risk, not because it is the most likely cause of civilizational disruption, but because it is one of the few natural processes that could cause it without any human decision being involved. Most catastrophic risks that researchers and governments focus on involve human choices. Nuclear weapons, engineered pathogens, AI systems developing in unexpected directions. These are risks that could, in principle, be avoided if humans chose differently. Yellowstone cannot be negotiated with. It cannot be regulated or deterred. It will do what the geology does, on the geology schedule. This puts Yellowstone alongside asteroid impacts and large-scale pandemics, natural processes operating on timescales that human civilization has never had to seriously contend with. Our tools of risk management, insurance, international coordination, early warning systems are only partially applicable. The Yellowstone Volcano Observatory represents something rarer than it should be. A government agency watching a piece of ground around the clock, not because it expects catastrophe, but because the cost of not watching is too high to accept. A major eruption at Yellowstone would not be a surprise in the way the 1953 North Sea flood was a surprise. There would be time to respond. Whether time to respond translates to time to protect people at the necessary scale is a different question, one that also doesn't have a confident answer. The broader category of geological risk that Yellowstone represents, low probability, extreme consequence, essentially unpreventable, is one that risk management theory handles poorly. Standard risk frameworks multiply probability by impact to get expected harm. A 1 in 700,000 annual probability, even multiplied by a civilization-scale impact, produces a number that gets lost in comparison to the much higher probabilities of everyday risks. This is why governments consistently underfund preparation for rare catastrophic events relative to their actual expected cost, and why the argument for taking Yellowstone seriously has to be made on grounds other than expected annual harm. The comparison to the Cascadia subduction zone, the fault system running along the Pacific coast of the United States and Canada, is instructive. Cascadia has a roughly 1 in 50 annual probability of producing a major earthquake and tsunami, orders of magnitude more likely than a Yellowstone supereruption. FEMA estimates such an event would kill 13,000 people and injure 27,000 in the immediate impact. Pacific Northwest governments have been aware of this risk for decades and have made significant investments in preparedness, though most analysts consider those investments still inadequate. Yellowstone, with its smaller annual probability, receives less political attention as a result. The mathematics make sense. Whether the mathematics is the right framework for thinking about risks of this kind is a different question. Yellowstone's last full eruption happened before our species existed in its current form. Anatomically modern Homo sapiens appear in the fossil record around 300,000 years ago. The Yellowstone caldera is 640,000 years old. The event that created it happened to creatures that were not quite us yet. And yet, here we are, putting seismographs in the ground, measuring uplift to the centimeter, publishing weekly bulletins, watching something that doesn't know we exist, with instruments we've had for less than a century, hoping to detect in advance something that hasn't happened since before we were human. The ground at Yellowstone will keep moving. The earthquakes will continue. The geysers will erupt on their own schedules. The magma will shift and pulse beneath the surface, or not. The USGS will publish its weekly bulletin, and at some point in the geological future, near by geological standards, incomprehensibly distant by human ones, something will happen under that plateau that makes everything we've built look like what it actually is: temporary. Yellowstone doesn't let you forget that. There is something worth sitting with in the fact that we are the first human civilization to know what Yellowstone is. Every human population in North America before us lived in proximity to Yellowstone without understanding what it was. The peoples who crossed from Asia, the cultures that built Cahokia and Chaco Canyon, the nations that lived near the Rockies for 10,000 years. None of them knew what the ground beneath them was capable of. They saw the geysers, they felt the earthquakes. Some traditions carry stories of the land being alive, but the specific knowledge that beneath this plateau sits a magmatic system capable of altering the global climate is less than a century old. The first serious geological study of Yellowstone's volcanic nature began in the 1960s, when Bob Christensen of the USGS looked at the topography and realized that the entire Yellowstone Plateau was the floor of an ancient caldera. The insight required looking at satellite imagery, something that hadn't existed before. Before that, geologists had mapped the individual features of the park without understanding the system they were part of. We have known what Yellowstone is for roughly 60 years. We have been watching it continuously for 25. On the timescale of the geology, we just arrived.